Cavitation tests are being done on a model pump with an impeller diameter of 20 centimeters and an inlet pipe diameter of 8 centimeters. Pumping water at 80 degrees C and running at 2400 RPM, it is observed to cavitate when the static pressure at the inlet is 80 kPa and the flow rate is 2000 liters per minute. Find the required NPSH of a prototype pump that is 4 times larger and runs at 1000 RPM while pumping water at the same temperature. So this is a pump scaling question, but it's also concerned with the required NPSH. So remember, NPSH is the net positive suction head, and that's a characteristic of a pump that determines whether or not it's going to cavitate in different applications. So what's happening here is a pump manufacturer is doing a test on a model pump, so a smaller pump, where tests are easier to do, and using the results to predict the performance of the large scale or prototype pump. So we'll start by summarizing the given information. So we have a model pump undergoing cavitation tests. So we'll summarize the data. The diameter of the model is 20 centimeters. The inlet diameter of the model is 8 centimeters. The temperature is 80 degrees C. The speed of the model is 2400 RPM. The pressure at the inlet for the model is 80 kPa. And finally, the flow rate for the model during these tests is 2000 liters per minute. Now, a couple other things that are given. We know the ratio of the diameter of the prototype to the diameter of the model is 4, and we know that the prototype is running at 1000 RPM. So that's our given information. Lots of information about the model being tested for cavitation, and a bit of information for the prototype. We know how big it is, and we know how fast it's running. So what we're asked to find is the required NPSH for the prototype. So we'll list our assumptions. And the assumptions we'll be making are steady state, incompressible constant temperature, and that the pump scaling laws apply. Now for the analysis. So we'll begin by looking at the model, and in particular we'll use the definition of NPSH to calculate the NPSH requirements of the model. So we're looking at the NPSH required, and I'll put a superscript model on here to remind us that's what we're looking for. And the definition of NPSH is the pressure at the inlet minus the vapor pressure at the inlet, divided by rho g to get it as a head, and then plus the kinetic head as well. So that's V inlet squared over 2g. Now the pressure at the inlet we were given as part of the given information. The vapor pressure and the density we're going to have to look up, and we're going to have to calculate the inlet velocity. So the vapor pressure and density are a function of the temperature. So we're at 80 degrees C. And remember, this is water, so the vapor pressure is equal to 47.39 kPa, and the density is equal to 971.72. And lots of places you can look that up. I looked that up in table A2 of the thermodynamics textbook, Morin and Shapiro. So those are the properties that we need. Other thing we need is the velocity at the inlet. Well, we know the volume flow rate and we know the area of the inlet. So the velocity of the inlet will be that volume flow rate divided by the area of the inlet. And the volume flow rate was 2,000 liters per minute. Divide that by 60,000 and we'll get meters cubed per second. And then divide by area, pi by 4, times the diameter is 0.08 meters, or 8 centimeters squared. And that gives us a velocity of 6.6315 meters per second. So now we have everything we need to calculate the NPSH of the model. So we'll do that now. And when we do that, we get 5.6623 meters. So that's the NPSH requirements of the model expressed as a head. So now we need to use the pump scaling law to get the NPSH of the prototype. So the pump scaling law we're interested in is the one that talks about the ratio of the heads for the prototype and the model. So the head of the prototype divided by the head of the model is related to the speed ratio, n prototype over n model squared, times the scale, dp over d model squared. So this is a general scaling law that talks about a ratio of heads, and usually we use this when we talk about the head developed by the pump. But realize that the ratio of the head developed by the pumps is the same as the ratio of any two other heads. So we can use this for NPSH as well. So these two heads can be a ratio of NPSH required. So that allows us to calculate the NPSH required of the prototype. So we'll get NPSH required of the prototype will be equal to NPSH required of the model. We're just bringing this up to the other side, multiplied by the ratio of speeds, NP over NM squared, times the ratio of sizes, dP over dm squared. And we know everything on the right hand side of that equation. So this is our 5.6623 meters. The prototype is running at 1,000 RPM. And the scale is 4. That was given to us directly. We were told the prototype is 4 times as big as the model. So that gives us an NPSH for the prototype of 15.729 meters.